This is the algorithmic landscape from 50 algorithms every programmer should know. If we look at the classification family, right next to the traditional decision tree, we find its direct evolution, algorithm number 31, the random forest. Instead of relying on a single model to categorize our data, this algorithm trains an entire voting committee of hundreds of models to make decisions together. This graph shows why that committee is necessary. The jagged orange line represents a single decision tree trying to fit the data points. It captures every outlier, treating random noise with the same importance as the true signal. In statistics, this is called high variance. It makes the model fragile. If we alter just a few rows of the input data, the tree redraws its logic to chase the new noise. The engineering challenge is to retain the flexible mapping power of a tree while stripping away this instability. A solitary decision tree is too fragile to trust on its own. To handle complex data, we must abandon the search for one perfect model. The macro solution is to grow hundreds of different trees and average their predictions together. But there's a requirement for this ensemble to work. The trees must be de-correlated. If we average 100 identical trees, we get the exact same errors. The ensemble gains predictive power only if the individual trees make different mistakes and disagree. Here on the right, averaging diverse models cancels out individual errors, leaving a smooth violet curve, the true underlying pattern. Combining models maintains accuracy but shrinks instability. As the variance equation shows, lowering tree correlation shrinks the forest's variance. Random forest transforms disagreement into a tool, showing that a diverse crowd of models is more robust than a single fragile expert. The algorithm forces disagreement through mechanical randomness. First is bagging, building each tree with a random subset of data rows. The unselected out-of-bag rows act as a built-in validation set. Next, feature subsampling. At every branch, trees only examine a tiny random fraction of columns. This forced blindness is strategic. It prevents one dominant feature from forcing every single tree into making the exact same split at the top. The result is a forest where every tree is unique. Because they were fed different data and given different options, they are pushed to ask different questions to solve the same problem. When new unlabeled data is fed into the forest, it flows down all parallel paths at once, receiving independent predictions from every unique tree. In the final aggregation step, the algorithm tallies the individual votes. The majority class becomes the ultimate answer. Injecting targeted randomness into the training pipeline is the filter required to extract a stable signal from chaotic noise. Bag the rows, randomize the features, grow the trees deep, and average the vote. These mechanics make Random Forest an out-of-the-box solution that handles messy tabular data without falling into the trap of overfitting. Now that the mechanics are clear, it's time to move from theory to implementation. Guess exactly how many lines of code it takes to spin up hundreds of voting trees, and we'll see if you're right in the coding segment. Bag the rows, randomize the features, grow the trees, and vote. Here is how few lines of scikit-learn it actually takes. We are using a dataset called socialnetworkads.csv. Our objective is straightforward. Predict the binary purchased target, determining whether or not a specific user bought a product based on their profile. The initial pipeline relies on pandas for the data import. We immediately drop the user ID column. It is a strictly identifying field that contains no repeatable predictive patterns. Next, we address the gender column. Machine learning models require continuous mathematical inputs, so we use one-hot encoding to convert these distinct text categories into a numerical format. This leaves us with our independent feature matrix, X, containing the processed gender, age, and estimated salary fields. We isolate the purchased column into a separate dependent target vector, Y. We then pass these structures into train test split. We assign 75% of the data to the training partition, reserving the remaining 25% as a pristine testing partition to validate the model later. Finally, we apply a standard scaler. This normalizes the numeric distributions across our features, ensuring that larger numerical scales, like a $50,000 salary, do not mathematically overwhelm smaller scales, like an age of 25. This diagram illustrates the algorithm's exact starting point. We now have our scaled training set, strictly defined by n rows and d features. All of this data wrangling is the necessary prerequisite labor. It provides the clean, normalized matrix required to actually begin the bagging process. To build the model, we instantiate the random forest classifier class from the sklearn.ensemble library. This visual compares a standard single decision tree on the left against a complete random forest architecture on the right. Because an ensemble is a collection of independent models, we need specific parameters to dictate how this grouping is generated. We set n_estimators equal to 10. This parameter explicitly defines the exact number of independent decision trees to be grown in our forest. Instead of seeing the entire dataset, each of these 10 estimators receives its own distinct randomized bootstrap sample drawn directly from the training matrix. We then set max depth to 4. This acts as the primary regularization constraint to explicitly halt vertical tree growth. By limiting the depth to 4 levels, we actively manage the bias variance trade-off. This cap prevents individual trees from growing too deep and memorizing the noise present in the training data. Next, we define the criterion as entropy. This forces the algorithm to score potential node splits based on information gain, seeking the mathematical division that creates the most homogeneous branches. This flowchart details the hidden algorithmic mechanism triggered during those splits. At each branch, the model evaluates only a random subset, the square root of d, of the total available features, guaranteeing that no single strong feature dominates the ensemble. With the constraints set, we execute the process using classifier.fit. Because every tree relies solely on its own isolated data bag and its own feature subset, they require no communication. This makes the fit process embarrassingly parallel across the hardware. Once training finishes, we transition to the inference phase by running ypred equals classifier.predict. During this step, a single unseen test row is pushed down through the branches of all 10 trained trees simultaneously. Each tree yields its own classification, and those 10 independent results are immediately collected into a single prediction array. This diagram shows how the system arrives at its conclusion. The final output is mathematically selected by calculating the statistical mode, taking the majority vote of that prediction array. These two simple method calls condense dozens of complex parallel operations into a single output variable, entirely masking the massive computational labor happening underneath. We evaluate the model using the sklearn.metrics module. The resulting confusion matrix yields 64 true negatives and 29 true positives, against only 7 total misclassifications. Out of the box, with virtually no hyperparameter tuning, the algorithm achieves an accuracy score of roughly 93%. Looking past the accuracy score, we must evaluate the computational efficiency. How exactly does this algorithm process multiple models at such high speeds? The average training time complexity relies on B trees, N rows, and D features. The resulting runtime scales as big O of B times the square root of D times N log N. If the data forces the trees to become fully unbalanced, the worst-case training complexity balloons to big O of B times D times N squared. For inference, the prediction time complexity drops to big O of B times the maximum depth, which generally approximates to big O of B times log N. Finally, the space complexity required to store the physical forest in memory is simply big O of B times the total number of nodes. The square root of D feature subset is the dual-purpose optimization at the core of the algorithm. It serves as both the mechanism that prevents overfitting and the mathematical shortcut that slashes training time. Just 10 trees, 4 lines of code, 93% accuracy. That is the appeal of the forest as a default.
But 4 lines that score 0.93 on a toy dataset is one thing. Where does a forest actually earn its keep in the real world? And when exactly should you not reach for it? That is precisely the critical question we will answer next. To verify this code mapping yourself, you can review the complete execution notebook at this source repository. 4 lines of code, and you understand why data scientists reach for random forest first. You interact with this algorithm every time you use a credit card. Banks rely on it to generate your credit score and flag fraudulent transactions in real time. Telecom companies deploy it to predict which customers are likely to cancel their service. Up in orbit, satellites use it for remote sensing, classifying vast stretches of land from space.
This diagram shows how the algorithm operates in medical diagnosis. By tracing these branching paths of symptoms and test results, the model arrives at a definitive cancer or non-cancer label. It also provides a metric called feature importance. In bioinformatics, researchers use this ranking system to sort through thousands of biological markers and isolate the specific genes most responsible for a disease. By ingesting complex data and returning usable insights with minimal friction, Random Forest has become the industry's default starting point for tabular analysis. The forest as a whole arrives at a more stable truth. This diagram highlights an elegant byproduct of the bagging process, out-of-bag or OOB error estimation. Because the data subsets are drawn randomly, a portion of the original data is left completely untouched by each tree. Since about 37% of the rows are never seen by a specific tree during training, those rows act as a natural test for that tree's accuracy. This provides an unbiased generalization estimate without needing a separate holdout set. This graphic compares model transparency. A single decision tree is a white box. You can read its logic, but scaling up to a large forest creates a black box. The volume of voting trees makes it difficult to explain the reasoning behind any prediction. That volume also introduces memory weight. Large forests are storage-heavy because every individual tree must be saved and loaded for inference. Furthermore, the algorithm struggles with extrapolation. Because its predictions are bounded by the averages of its training data, it cannot forecast values beyond the range of what it has already seen. These limitations define the engineering red lines. Random Forest is the wrong tool for high-dimensional sparse data or environments requiring instant, ultra-low memory inference. This dashboard maps where algorithm number 31 sits within the broader 50 algorithm landscape, positioned among the other primary classification tools. It is one of the key methods detailed in the book 50 Algorithms Every Programmer Should Know by Imran Ahmad. While Random Forest uses an averaging approach to mitigate errors, the next evolution in machine learning takes a different path, correcting those errors sequentially. That leads to gradient boosting, algorithm number 32. Instead of building independent models that vote, it builds a sequence of trees correcting the predecessor's mistakes. Random Forest serves as a high-performance baseline for tabular data, but when a project requires squeezing out every last percentage point of accuracy, the industry moves from the forest to the boost.